Assalamualaikum warahmatullahi wabarakatuh, and see you again. In this video, we are still looking into chapter 5 on specific chi-square test, but in part 2, where we will explore at a number of examples on goodness of fit test. Let's look at the first supplementary example in the subsequent slide. This example is from a past assessment. An aircraft undergoes a complete scheduled annual inspection at 5 standard time intervals labeled A, B, C, D, and E, with failure rates at these intervals are known to follow a Crowe-Amsa model as 29.8%, 20.4%, 17.9%, 16.5%, and 15.4%. A set of group test data was carried out, and the observed number of failures from all 5 intervals are recorded in the table below. Test at 5% significance level to see whether the set of group test data fits a Crowe-Amsa model. From this question, notice that you are to test whether the set of test data fits or follow the specific Crowe-Amsa model. That is, you are to perform a goodness of fit test at 5% level of significance. The model or distribution assumed under the null hypothesis H0 should be as stated here. In this example, the probabilities Pi are given for all I equal to A, B, C, D, and E. For example, PA is 0.298, PB is 0.204, and so on. Therefore, no parameter to be estimated in this example since Pi are all known. Please check and make sure that the sum of the percentages must be 100% or equivalently the sum of proportions must be equal to 1. How are you going to proceed from here? Let's find out in the next slide. Continue resolving the supplementary example 1. The null hypothesis H0 should be written as follows, where the set of group test data fits or follow the Crowe-Amsa model, that is, PA is 0.298, PB is 0.204, and so on, as stated in the question. Whereas under H1, the data do not follow the Crowe-Amsa model, that is, at least one of the percentages or proportions is different from the stated value. Since we know this is a goodness of fit test, then the rejection or decision rule is only one, that is, to reject H0 if chi-square test is greater than chi-squared alpha nu. We know alpha is 0.05 or 5% level of significance. What about nu? By definition, nu in a goodness of fit test is k minus p minus 1, and since we know that all the pi values are given for all I equal to A, B, C, D, and E, then we do not have to worry on what parameter to be estimated. In short, the number of model parameters to be estimated denoted by P is 0. Hence, the degrees of freedom nu is k minus 1. Now, what is the value of k? We cannot simply say k is 5 just because we have 5 intervals A, B, C, D, and E. We can only know for certain what the value of k is after we check and make sure that the expected value for all classes are at least 5. So, we need to calculate the expected values first, which are shown in the following slide. To solve a goodness of fit test question such as in the supplementary example 1, we can list down the given and necessary information in a table so that the process of getting the chi-square test statistic value is clearer. In this example, We know the ith classes are A, B, C, D, and E, and the corresponding proportions are as given in the question, where the percentage values are changed into proportions. Next, you can list down the respective frequencies or observed values in the table. After listing the OI values, since the PI values are known, you can immediately list down the corresponding expected values EI, where EI is N, which is 49 in this example, multiplied by the respective PI. As we know, the sample size N is also the total frequencies or the total observed values OI. At this stage, please be careful when you calculate EI. It is neither N times OI, nor it is PI times OI, but the EI is N times PI. Many students have made this kind of careless mistakes in the past. After calculating and listing down the EI values, please do not forget to check whether each of EI is at least 5. As you can see from the table, yes, all EI values are more than 5. Therefore, you can now be certain that the value of K is 5, and hence the degrees of freedom nu is 5 minus 1, which is 4. Before going to the last column to calculate the chi-square test statistic value, please also do not forget to check that the sum of EI must be the same as the sum of OI. Summing up all the values in the EI column, you can see that the sum of EI is the same as the sum of OI. Therefore, you can start calculating the value in the last column, which are the squared differences between OI and EI divided by EI for all I equal to A, B, C, D, and E. Summing up all the values in the last column, you will have a chi-square test statistic value, which is 5.4437 in this example. Please recall the rejection rule for this example is to reject H0 if the chi-square test statistic value is greater than the right-sided critical value chi-square 0.05 nu, where nu is 4. Here the critical value at alpha equal to 0.05 and nu equal to 4 is 9.4877. Since the calculated chi-square test statistic value is 5.4377, which is obviously less than 9.4877, we do not reject H0 and conclude that at alpha equal to 0.05 level of significance, the set of group test data does fit the Crow-Amsa model. What if you have EI being less than 5? In such a case, you should combine the class which has EI less than 5 with its nearest neighboring class, either a class before or after, until the combined EI is at least 5. Let's look at the following simple example. Suppose OI and EI are listed as follows. Notice that the last EI is 4, which is less than 5, and hence the number of classes K is not simply 5. To identify what K is, what you need to do first is to combine the last class with its neighboring class, which is a class before. After combining the last two classes, the new EI is 10 and so the new OI is 12. At this stage, all EI values are at least 5, therefore K is 4. The last column values can then be calculated, which leads to the correct test statistic value. If you have more than one class which have small expected values, you can repeat the combination until the new EI is at least 5. The expected value EI being less than 5 can also occur in the beginning or in the middle of the table. The same concept still applies where you can combine the class with its preceding or subsequent neighboring class. The combination can only be done if EI is less than 5. Please do not combine classes if only OI is less than 5. Let's look at the supplementary example 2, which is a past final exam question. The number of computer malfunctions per day is recorded for 300 days and the results are tabulated below. The number of computer malfunctions per day is claimed to follow a Poisson distribution with a mean of 1.3. Do we have enough evidence from the data to reject the claim at significance level alpha equal to 0.1? Again, we have a goodness of fit test here, since we are to investigate if the sample data provide any evidence to reject the claim that the computer malfunctions per day follow a Poisson distribution with a mean of 1.3. Therefore, under the null hypothesis H0, the number of malfunctions denoted by X is assumed to follow a Poisson distribution with mean 1.3 per day, whereas under H1, X does not follow the assumed Poisson distribution. Since we know the value of this distribution parameter, which is lambda equal to 1.3, from where we can calculate the ith class probability values, or PI, used in the calculation of the expected values EI, therefore, the number of parameters to be estimated, which is denoted by P, is 0, and hence the degrees of freedom nu is k minus 1. What are the ith class probability values Pi and the corresponding expected values EI? Let's find out the answers in the following slide. Continue with the solution for supplementary example 2. Here we have the ith classes where the ith values start from 0, 1, 2, and so on, which are exactly the values of X, which denotes the number of computer malfunctions assumed under H0 to follow a Poisson distribution with mean 1.3 per day as highlighted in the previous slide. Unlike in supplementary example 1, in this example, we do not have the values of Pi given directly. Instead, we need to calculate or find out the Pi values first based on the distribution assumed under H0, which is Poisson with lambda equal to 1.3. Remember, Pi is the probability that X is equal to I. Therefore, we can get the Pi values for I equal to 0, 1, 2, 3, and 4 directly from the Poisson probability function stated on page 1 of the statistical table booklet. Alternatively, you can also work out the probability that X equal to I by calculating the difference between two successive cumulative Poisson probabilities from the statistical table booklet, page 25, when lambda is 1.3. Please recall the skill that you have learned on finding probabilities of Poisson random variable in chapter 1. You may calculate and check the values of Pi that should be as follows. For the last Pi value, this is the probability that X is at least 5, which is 1 minus probability of X being at most 4, or simply 1 minus the sum of earlier probability values. You must make sure that the sum of all these probabilities Pi must equate to 1. The observed values OI can be stated directly in the next column as what are given in the question. The next column is the values of EI defined as 300 times the corresponding values of Pi that have been calculated earlier. You can check that the EI values should be as follows. Notice that the last EI value is 3.21, which is clearly smaller than 5. Therefore, we need to combine the last class with the earlier preceding neighboring class so that the new EI and OI are given by 12.93 and 18 respectively. Since all values of EI are already at least 5 at this stage, then we can settle with the finalized number of classes k equal to 5, not 6, and hence the degrees of freedom nu for this example is 4. After making sure that both sums of nu, OI, and EI are the same, next you can calculate the last column values and obtain the chi-square test statistic value, which is the sum of the squared differences between the nu, OI, and EI divided by the corresponding nu, EI. Here, the correct chi-square test statistic value is given by 8.1005. What are the decision and conclusion that we can make based on this chi-square test statistic value? Let's proceed to the next slide for the answer. Let's look at the complete solution for supplementary example 2. From the earlier slide, we already knew that the degrees of freedom nu is 4 and we should perform the goodness of fit test at the level of significance alpha equal to 0.1 or 10%. The rejection rule is then reject H0 if chi-square test statistic is greater than the right-sided critical value chi-squared 0.14, which is given by 7.7794 from the statistical table booklet page 36. As the chi-square test statistic value was calculated to be 8.1005, which is slightly greater than 7.7794, then the decision is to reject the null hypothesis H0 and conclude that at alpha equal to 0.1 or 10% level of significance, we have enough evidence from the data to reject the claim that the number of computer malfunctions follow a Poisson distribution with mean 1.3 per day. That is, we have evidence that X does not follow a Poisson distribution with mean 1.3. What if we reduce the level of significance from 10% to 5%? That is, alpha value now is 0.05. The corresponding critical value is chi-square 0.054 given by 9.4877. Therefore, the chi-square test statistic is now smaller than the new critical value at the reduced level of significance, which indicates that we fail to reject H0 and hence change the conclusion where at the reduced level of significance alpha equal to 0.05, we do not have enough evidence from the sample data to reject the claim. Let's look at the supplementary example 2 again, but this time suppose the parameter value is not given. What we only know is to perform a goodness of fit test on whether the number of computer malfunctions per day follow a Poisson distribution or not. Therefore, under H0, the number of computer malfunctions denoted by X is assumed to follow a Poisson distribution with the unknown parameter lambda. And under H1, X does not follow the Poisson distribution. Since lambda is unknown, then we need to estimate lambda first before we can calculate the PI, followed by EI and the chi-square test statistic values. In this case, the number of parameters to be estimated denoted by P is 1, and hence the degrees of freedom nu is K minus 1 given by K minus 2. Now, how are we going to estimate lambda? Let's find out the answer in the subsequent slide. We know that the Poisson distribution is characterized by one parameter, which is lambda. But what is lambda? Recall, lambda is the mean or expected value of a Poisson random variable. So, to estimate lambda is to calculate the mean or expected value of x based on the given data. Since we have a frequency table where each value of x has its own frequency, then the estimated lambda is the expected value of x given by the sum of the frequencies fi multiplied by the corresponding xi values divided by its corresponding frequencies fi over all I values. Therefore, in this example, the estimated lambda is calculated as follows, and its value is given by 1.3833, which is correct to 4 decimal places. Notice that for the last value of x, which is supposed to be at least 5, we only take the marginal value, which is 5, in the calculation of estimated lambda. Using this estimated lambda value, then under the null hypothesis H0, we can write the number of computable functions denoted by x follows a Poisson distribution with mean 1.3833 per day, while under H1, x does not follow the Poisson distribution with mean 1.3833 per day. Using the distribution stated under H0, you can repeat the same procedure for getting the values of Pi, which can be used to calculate the values of Ei and finally the value of chi-squared test statistic. Since estimated lambda value is up to 4 decimal places, then you can only use the probability function formula to calculate the Pi values. You may want to calculate on your own and check if you get the same values of Pi and Ei as given in the following table. Please notice that the problem of Ei being less than 5 still occurs in this revisited example. So, you need to combine the last two classes so that the degrees of freedom nu is 5 minus 2, which is 3. The chi-squared test statistic value is then around 6.4105. At the 10% level of significance, we will reject the null hypothesis H0 if the chi-squared test statistic is greater than the chi-squared 0.13 given by 6.2514. Using this estimated lambda value, we still come up with the same decision and conclusion at 10% level of significance, where we have evidence from the sample data to reject the claim that the number of computable functions follow a Poisson distribution with expected mean of 1.3833 per day. Let's look at the last example on goodness of fit test in this video. This example is also one of the past final exam questions. It is believed that the lifetime of all batteries follows a normal distribution with mean 33 and standard deviation 2.91. A random sample of 175 batteries revealed the following distribution of battery lifetime in months. The questions are: first, determine the values of A, B, and C, and second, test the above belief at the 10% level of significance. Suppose we define a random variable x to represent the lifetime of the batteries. Then under H0, x is assumed to follow a normal distribution with mean 33 and a variance 2.91 squared, whereas under H1, x is assumed not to follow the stated normal distribution. Using the distributional assumption under H0, then you can solve the question in part 1 to determine the values of A, B, and C using the same approach that you could have done to find the probability values for any normal random variable. The probability values listed in the first column of the table are the values of Pi for x, which is a continuous normal random variable. Using these PI values, you can then proceed to answer the question in part 2 as shown in the next slide. The answers for part 1 are given as follows. Here, after standardization, the answers for A and C are the same, whereas the answer for B can also be found by taking one minus the other probability values, so that the sum of probabilities will be equal to 1. The answer for part 2 can start with writing the hypothesis statements, where, as mentioned before, under H0, the battery lifetime denoted by X follows a normal distribution with mean 33 and variance 2.91 squared, whereas under H1, X does not follow the stated normal distribution. As the two parameters mu and sigma squared in the normal distribution are known, then the number of parameters to be estimated, denoted by P, is 0. The probability values obtained in part 1 can be listed in the PI column as shown in the following table, where PI in this example is the probability that X is within the specified interval. Multiplying the PI values with the total frequency, which is 175, you will obtain the expected values EI. Notice that the first and last EI are smaller than 5. Therefore, you need to combine the respective classes with their neighboring classes. The first class is merged with the second class, whereas the last class is merged with the second last class. Hence, we have the new sets of OI and EI values as listed in the following table, where the two combined classes now have the expected values being more than 5. Therefore, the finalized number of classes denoted by K is 7, and hence the degrees of freedom nu, which is defined as K minus P minus 1, is 6 in this example. Do we have any evidence from the sample data to accept the belief that the battery's lifetime follows the stated normal distribution? Let's proceed to the next slide to complete the answer for part 2. Having calculated the test statistic value in the previous slide, now we can compare this test statistic value with a critical value in the rejection criterion, where we will reject H0 if the chi-squared test statistic value is larger than the critical value chi-squared 0.16 given by 10.6446. Since chi-squared test is 7.0352, which is smaller than the critical value, then we do not reject H0 and conclude that at alpha equal to 0.1 or 10% level of significance, we have evidence from the sample data to accept the belief that the lifetime of the batteries does follow a normal distribution with mean 33 months and standard deviation 2.91 months. We finish with goodness of fit test topic, which is the first out of 3 topics under chapter 5. Let's do a checklist on this topic. At the end of learning this topic, you should be able to first identify the PI values if these values are given directly. If not, you must know how to calculate the PI values based on the distribution assumed under the null hypothesis H0. Second, you should be able to state the null and alternative hypothesis correctly. Remember, under the null hypothesis, you always assume that the random variable follows a particular distribution. Third, you should be able to identify the values of P, which is the number of parameters to be estimated, K, which is the finalized number of classes, and hence nu, which is defined as K minus P minus 1. Next, you should also be able to calculate the expected values EI correctly by multiplying the total frequency N with the corresponding PI values. And do not forget to combine classes if EI is smaller than 5. Having sure all EIs which are at least 5, and the sum of OI and EI are the same, you should then be able to calculate the chi-square test statistic correctly. And finally, you should be able to perform the goodness of fit test according to the standard testing procedure where all elements in the test are included, such as the decision rule, decision statement, and conclusion. That's it from me, and we'll meet again in part 3 of this chapter on independence and homogeneity tests. Until then, Assalamualaikum warahmatullah, and thank you very much for watching.